Remember how we define the length or norm of a vector. We have an interesting theorem to impose now. The Cauchy-Schwarz inequality say if you have two vectors like u and v in Rn or n space, then for sure you can say that the absolute value of u dot v, the absolute value of the dot product between u and v, is less than equals to magnitude of u times magnitude of v. But how do we prove this statement? We're going to go back to discrete math and define universal statement, implication, and how to use the direct definition to prove a universal statement. Suppose Qx be a predicate, which is basically a statement in X, and D is the domain that X comes from. The universal statement is a statement of the following form. For any X, for all X, this guy is called the universal quantifier in domain D, Qx. It is true if and only if Qx is true for every single X in D, and it is going to be false if you find a counterexample for it. So for example, let's take a look at this universal statement. It says for any X in R in real line, X must be more than 1 over X. This statement is not true because I can find a counterexample like X is equal to 1. 1 is not more than 1. So I found the counterexample here. So it is not necessarily true all the time. Now, if P and Q are two statements, the conditional of Q by P is if P then Q, or P implies Q, or P then Q, if P then Q. P is the hypothesis and Q is the conclusion. Now, in predicate form, let Px and Qx be two predicate with common domain D. The notation Px then Qx means that every element in the true set of Px lands in the true set of Qx, or equivalently for every x, Px then Qx. Now, method of direct proof. Express the statement to be proved in the form for every x in domain D, if Px then Qx. Start the proof by assuming x is a particular but arbitrary chosen element of domain D, for which the hypothesis Px is true. Then use the definitions to try to prove Qx. So in this case, your hypothesis is u and v are vectors. Your conclusion is this inequality. So let us begin. We're going to get rid of an obvious case first. Case 1. If u is 0 vector, then it follows that the absolute value of u dot v is the absolute value of 0 dot v, which is basically the absolute value of 0, which is 0. On the right-hand side, the magnitude of u times the magnitude of v is 0 times magnitude of v, which is basically 0. So you just showed that the absolute value of uv, which is 0, is less than equals to the magnitude of u times the magnitude of v, which is 0 again. So we just proved the statement for this obvious case. So again, this is for simplicity. We're getting rid of an obvious case. Now in case 2, we work with more general form. Suppose u is non-zero vector. Let us define t to be a real number and form the vector tu plus v. We're going to find the dot product between tu plus v by itself. Remember the properties for the dot product. This guy is non-negative. If you find the dot product between these two, you're basically distributing t into parentheses, then you distribute v into parentheses and simplify as much as possible. This becomes t squared u dot u plus 2t u dot v plus v dot v. It must be more than equal to 0. These are from the properties that you learned for dot product. Now for simplicity, I'm going to call u dot u a. I'm going to call 2 times u dot v b, and I'm going to label v dot v c. In a bit, you're going to see why I'm doing this. You can form a quadratic inequality. So at squared plus bt plus c is more than equal to 0. A is u dot u, b is u dot v, and c is v dot v. Now we are going back to algebra. We have a quadratic equation that is more than equal to 0, everybody. This is your quadratic equation. What's the meaning of the discriminant here? We're going back to algebra. Remember that if you have a quadratic equation, the discriminant has 3 different scenarios. B squared minus 4ac. If it's positive, then the graph crosses x-axis, and you end up with 2 solutions. If the discriminant is equal to 0, the graph touches x-axis at 1 point. And if the discriminant is negative, the graph is above x-axis, there is no intersection. Here we are assuming A is positive. That's why it opens up in all 3 cases. Now, b squared minus 4ac must be less than or equal to 0. So b squared is less than or equals to 4ac. Or what's the meaning of that for u and v? A is u dot u, b is 2u dot v, and c is v dot v. Replace them. You get 4u dot v squared less than or equals to 4u dot u times v dot v. Again, b is equal to 2 times u dot v. So raise it to the second power, you end up with 4u dot v squared less than or equals to 4 times u, which is u dot u, times c, which is v dot v. Now divide everything by 4. You end up with u dot v to the second less than or equals to u dot u times v dot v. Taking the square root of both sides, you get the absolute value of u dot v less than or equals to the square root of u dot u times the square root of v dot v, which is by definition is the magnitude of u times the magnitude of v. So we just proved the Cauchy-Schwarz inequality for vectors u and v.